Hello everyone, and welcome to today's live broadcast, Light Sheet Microscopy for Tissue Clearing Applications and 3D Live Fluorescent Imaging, presented by Bi-Chang Chen from the Research Center for Applied Science, Academia Sinica, Taiwan, Alon Greenbaum from the California Institute of Technology, and Orla Hanrahan from Ondor Technology. We are excited to bring you this educational web seminar presented by LabRoots and sponsored by Ondor Technology. Ondor is a world leader in scientific imaging, spectroscopy solutions, and microscopy systems. In 2014, Ondor was acquired by Oxford Instruments, a leading provider of high technology tools for industry and research. To learn more about Ondor, please visit www.ondor.com. I'm Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. Before we begin, I'd like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want and any time you want during the presentation. Just click on the green Q&A button located in the lower left of the presentation window and type your question into the box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. Also, please notice that you will be viewing the presentation in the slide window. To enlarge the window, just click on the screen icon located on the lower right. Finally, if you have trouble seeing or hearing the presentation, please click on the support button at the top right of the presentation window, or use the Q&A button to let us know that you're having a problem. Thank you. Now I'd like to introduce Dr. Bi-Chang Chen. Bi-Chang Chen received his BS and MS degrees from the Chemistry Department of National Taiwan University in Taiwan in 2001 and 2003, respectively. For the MS work, he worked on the mesoporous material synthesis under the supervision of Professor Zheng Yan Mao. In spring 2014, he became an assistant research fellow at the Research Center for Applied Science, Academia Sinica, in Taiwan. He is interested in developing fast, low phototoxicity, multicolor, and 3D detection for fluorescent living specimens with subcellular resolution imaging tools. Please join me in welcoming Bi-Chang Chen. I will now turn the presentation over to him.
Thanks for the introductions. So my name, it's my great pleasure so that I can get research that I have done in Dr. Eric Bez's group. And the project will be the Lattice light sheet microscopy, and I will focus on how we develop the technique and what's the application for that. So the Lattice light sheet microscopy is simply for the 3D live fluorescence imaging. So when we talk about the fluorescence, then we will know there's always a lot of trade-off for the live fluorescence imaging, especially for the spatial resolution, for the imaging depth, and for the temporal resolution. And of course, because we are now talking about live, so there is a phototoxicity, which is most key, which is most of the time killing all the experiments. And because we are doing the fluorescence, so all the parameters should be based on the photon budget. If you have the unlimited photon budget, then you can do a lot of things to get a very good resolution in spatial and time, and also the depth. So what's the challenges for the live imaging? Of course, we know the samples are alive and they are dynamic. So that means your imaging speed should be fast enough to catch all the motions. To avoid the motion blurring, so the imaging speed should be fast enough. And the second, we really need a 3D resolution, because now everybody talking about the 3D imaging. And most of the time in microscopy, the actual resolution is the most worst part. So at least how to make an isotropic resolution in 3-dimensional, that's what we want to do. And the third one, we have a limited photon budget, because each photophore can emit how many photons is already determined by the molecule itself. So how can we manipulate all of these photons budget over time when we're doing acquiring the imaging? And the last one is the aberrations, which is kill all the optics, because when we use the light, and the light should be penetrated through the tissue, and as we know, laser scattering, absorptions. So the aberrations, all of these will be kind of problematic for the live imaging. So these are all the challenges. So the technique that we invent for we call the plane illuminations. What's the difference from the plane illuminations versus the epi illuminations? If you look at the plane illuminations, the plane illuminations will be like two objectives, and these two objectives will be orthogonal to each other. So we separate the excitation and detections. So if you look at we can send the laser from the side, and this side which is a plane, and this plane is the focal plane of your detection objective. So that means we can simply look at one plane by plane. And for the epi illuminations, we have like a single objective. We shine the laser and we correct the laser from all the depths. So that means there is no optical sectioning for the epi illuminations. But the good thing for the plane illuminations, we have a very good optical sectioning capabilities, and we can improve the actual resolutions, which is what we most concerned. But the good thing for the plane illumination and epi illuminations, we have a very good imaging speed because we use a wide field detections. So for the next slide that we will see a key trade-off. So there are a lot of different types of the plane illuminations. And what's the trade-off? So there is a trade-off for the light sheet thickness and the field of view. So if you look at this slide, we send the excitation. We make the excitation a very small optical spot, and then we can create a long light sheet. But the problem is the thickness. The thickness will be fat. So this is kind of if it's fat, that means it's kind of wide field again. So that means your actual resolution will not as good as the thin light sheet. But if you want to make a thin light sheet, then what you will have is the field of view become smaller. So these two are the trade-off. So long light sheet and the thickness is thick, and small light sheet, and you have a very good optical sectioning. So these are the kind of trade-off between what we call the Gaussian light sheet. So in our aerobatics group, we invent another optical properties we call the basal beam excitations. So the basal beam is kind of ring excitation over here. So if you send a ring, then actually at the focal plane is a basal function. So the objective itself is doing the Fourier transform. So if you send a ring excitation after the Fourier transform, it's a basal function. The basal function is very long and very thin light sheet. So for this kind of light sheet, then we can get a large field of view and then very good optical sectioning. So that's why first we do the basal beam microscopy. So this is kind of slides that we compare the Gaussian and the basal and the two-photon basal. If you look at the Gaussian is long, but the problem is it's the fat. So the actual resolution is not as good as the basal beam. But there is a problem for the basal beam is there are a lot of concentric ring. If you see in the middle of this slide, then you will see a lot of concentric ring. This concentric ring which will cause the background for us. So the first time we know, okay, how can we remove the background? So then we use the nonlinearity from the optics. So we use the pulse laser, and then we use the two-photon properties. By two-photon, because of nonlinearity, we can do the intensity square. So if you have an I square, simply we suppress the background by the two-photon basal. So this is the first technique that we invent for the two-photon basal. So this is a single beam. So single beam, how can create a plane? So we scan the beam very fast, back and forth. So by this way, we can create a time averaged plane illuminations. So this is one direction. For the next, we will see a movie, So for the actual resolutions, so we can do the scanning. So you will see the optical scanning is for the synchronize the objective scan. So you will see the excitation for the laser, and then the objective here is the focal plane of the excitation laser beam. So by this way, we synchronize these two, then we can see the 3D scanning by this way. This is we call the objective scan. And the other scanning mode, which we will see in the next movie, is the sample scanning. So simply, we can move the sample. We didn't move any optics, so we simply just move the sample itself. So by these two, we can get a really good 3D imaging by this way. So that's. So what's the another kind of manipulation that we can do is for the bezel beam, because bezel beam has a pre-pattern. So this pattern is that we can create some specific frequency pattern. So we can use the galvo mirror. The galvo mirror will be kind of step on and off, on and off, on and off. So to create some frequency on the excitation. So this is what we call the bezel beam super resolution by the structural illuminations. So if you look at the bezel function, and then if you use a galvo to step on and off, we can create the bezel SI, structural illumination excitation. So as you can see, this intensity plot, there is a frequency. So this frequency can be applied to your sample, and your sample can have modulated by this excitation pattern. And if you modulate, then we can get a lot of exposure. We can rotate the excitations, and then we can get a lot of exposure, and then we can reconstruct a super resolution imaging. So you can see here, there is a cell. This cell has a two color label, H2B and microtubules. So this is a 3D super resolution imaging based on the bezel beam excitations. So not just a single beam. If you do what's the problem for the single beam? Because if our exposure time is less and less, then each beam stay at one particular position will be very, very short. That means our signal to noise ratio is less. So in order to improve our signal to noise ratio, we have to put a lot of laser power. So that means we will kill our samples. So the phototoxicity and photo damage will happen. So how about we can create a multi-beam simultaneous by optics? So this is kind of the benefit for the multi-beam. First is the imaging speed, because we have multi-beam, so the imaging speed should be fast. And second, actually, the photo damage. Right now, we distribute one beam energy to many beam energy. So simply, we divide the 1/n of your number of your beams. Then we can keep the same signal to noise ratio, but we still keep the sample very happy. So this is the speed and photo damage. And this is kind of first the demonstrations for our multi-beam bezel. When we see the multi-bezel beams excitations, so this is the 7 parallel bezel beams with the diffractive optical element, and we use the diffractive optical element by these passive optics. The reason I call it passive is we cannot change it because this is a physical grating. So we put a bezel beam at a mask, and then we have a diffractive optical element. By this way, we can split one beam to 7 beams. So if you look at this intensity plot from the left panel, you can see all the different bezels. There's distance separations around 10 microns from each other. So there is no interference between each other. These all are 7 identical bezel beams. So by this way, we already demonstrate that the membrane, we can see an even larger field of view, and we can have a faster scanning, and we reduce the photo damage. That's the most important. We reduce the photo damage. So that means we can image the samples even longer. So this is the first time we say, okay, how about we do the multi-bezel beams? But we want to make even more beams. For example, like 100 beams, like 200 beams. But it's very hard to do the passive optics from the gratings. So we figure out a way. We use the spatial light modulator. So as you can see from this movie, you can see this is a bezel. So the bezel is there's a lot of concentric ring, we know, but the problem is the background. And we're looking at the So as you can see from the movie, if you can control the distance between each bezel beams, then you can have a very, very good optical properties we call the interference. As you can see, the pattern of the intensity pattern is keep changing. So you can see the different distance have some different interference patterns. At some specific distance, for example, like this case, around 0.91 micron, all the bezel beam has a constructive interference at the center and destructive interference from the side. So by this way, we can create a multi-beam bezel, and we can also reduce the background from the side loop. So the problem is how to create this kind of pattern, because we know the passive optics doesn't work. So we go to the active optics we call the spatial light modulator. So this is kind of scheme for the proposed setup. So you can see we have a binary spatial light modulator here from the 4 dimensions. So we calculate the intensity, and we kind of know the phase from the intensity, and then we apply this pattern to the spatial light modulators. And we have so after the first lens, then you can get this kind of diffracting patterns. And after the mask, we clear out the unwanted higher order diffractions. And we have 2 galvo mirror conjugate each other. One scan the X direction, the other one scan the Z directions. And then we conjugate this pattern to the excitation. And these 2 excitations, as we see, they are opposed. They are orthogonal to each other. And this is the point spread function that we can get from the optics, from the microscope. So the right one is the theoretical calculations, and there is the experimental data. So as you can see, they match pretty well. So this is what we kind of first time demonstrate a multi-beam and then bezel beam, and then they are doing a coherent interference. So these are all the experimental data. So as you can see, there's a single bezel, and then at a different distance, they have a different interference patterns. And for this one, as you can see from like a 1.6 micron, at this case, the background from the bezel function are suppressed, and all the energy are concentrated at the center. So this is what we want, and these are all the experimental data. And the reason we call it as a lattice excitation, lattice light sheet, because right now we can simulate any kind of lattice pattern, and then we apply to the spatial light modulator, and then we can get this kind of intensity pattern on the focal plane of the excitation objective. So as you can see, these are the hexagonal or cubic or square lattice patterns for all the different purpose. And it's, the most important is this is from the X and Z. And if you look at the scale bar over here, is the 2 micron. So that means we can control all the patterns at the sub-micron precisions. And these are very good for the for the structural illumination, because we know the structural illumination needs some frequency, and these are all the frequency from the lattice pattern, which is very good for the structural illumination for the super resolution. So here I will show you how we can construct this kind of the imaging core of the lattice light sheet microscopy. So we can send the light from the left one, there is a excitation objective, and the detection one is a huge one, is from the Nikon 1.1 NA numerical apertures. Both are deep in length, and we are doing the live imaging. So we dip these two objectives inside the imaging medium directly. So these two are very, very tight. So there is not enough space, and we customize a 5mm cover slip, so you can see the working area is very small, and we put the sample such as a sail or C. elegans or zebrafish on the focal plane. And if you look at the focal plane here, we put the dye solution inside. You can see all the light sheets. Now we can create 100 beams light sheets simultaneously, and each beam has a separation from around like 1 micron. So this is really good, because now we can improve our imaging speed and we can reduce our photo damages. So here I will show you animations for how can we get a 3D movie imaging by our scanning. So you can see a single, this is a leukemia cell, and the cell is labeled with a membrane marker. So as you can see, we have many beam light sheets, so we can shift, we can dither a little bit for the lattice pattern, and then we can create a time averaged uniform excitation for this very thin. The thickness of this light sheet plane is around 0.5 micron, which is very good for the cell. We can do a subcellular resolutions. So you can see we scan the sample, and then the beam, this plane doesn't move, and this plane is a wide field plane, so can be captured by the camera. So the camera will see a series of 2D TIFF data, and then we can stack all the 2D TIFF data, then we can get a 3D data for one time point. So if you want to do the time lapse, then we can do such as the next slide, we will see a movie for the cell which is moving on top of the cover slip. So this is a movie that we will see. So now we can play the movie for this. So you can see the cell is kind of curling on top of the cover slip. And if you look at all the different view angle, we didn't have any spatial resolution distortions. So simply we can get an isotropic resolution and this kind of subcellular resolution. And most important is, if you look at the timestamp, we can finish a 3D imaging at sub-second, less than a second. So we have a 5 millisecond exposure and then 150 Z slides. So we can get a very good temporal resolution for this kind of phenomenon. So here I will show you like we have two scanning mode. One is we call the dithered mode. The dithered mode is we can scan the beam and then get the imaging. And the other one we call a SIM mode, the structural immersion mode. We need to apply some specific patterns. We shift the pattern and we get the data. So by this way, we can get an even better spatial resolution. Of course, we lose some temporal resolution. So as you can see from this movie, then we will see the two different scanning modes, the dithered mode and then the SIM mode. So now we can play the movies. Then we will see what's going on for these two. So if you look at the left panel, you will see the dithered mode, which the time stamp with a second interval. But if you look at the right one, like a several second, like a 7.5 second interval. So as you can see, the temporal resolution is different. But the spatial resolution wise, you can see the right one, the SIM mode, has a better spatial resolutions. So we will back to our final slide is, again, this world is compromised it's a lot of trade-off between the spatial resolution and temporal resolution and also the imaging depth. The imaging depth, which I didn't cover a lot for this part, we still a lot of research is going on by using the light sheet and doing the even deeper tissue, for example, like the brain tissue, and then we can look at more to get a very fast imaging for the entire 3D for the brain constructing. And of course, most of the time we want to do the live imaging, so we have a phototoxicity. So again, this is a take-home message for the spatial resolution, temporal resolution, imaging depth, and phototoxicity. All of these parameters should be based on the photon budget, because we are doing the fluorescence. So I think there are still a lot of research, a lot of niche that we can do for all of these parameters. And hopefully, and all the researchers from the optics, from the biology, and from like biocomputations, we have to jump together to do a lot of extensive collaborations to make this beautiful data work. And thanks for your attention.
Thank you, Bi-Chang Chen, for that informative presentation. Now I'd like to introduce Dr. Alon Greenbaum. Dr. Greenbaum holds his BS and MS degrees in electrical engineering from Tel Aviv University and his PhD in electrical engineering from the University of California, Los Angeles. In his doctorate degree, Alon conducted biophotonics research under Professor Adouan Ojan, focusing on high-resolution and high-throughput microscopy for biomedical applications. In Professor Viviana Gradinaru's lab at the California Institute of Technology, he is exploring innovative imaging techniques for various neuroscience applications. I will now turn it over to Dr. Greenbaum.
Thank you for the kind introduction. So my advisor is Professor Viviana Gradinaru, and I'm from the California Institute of Technology. Today I'm going to talk about light sheet microscopy for tissue clearing application. I joined Professor Viviana Gradinaru's lab something like 8 months ago, and I built a light sheet for that purpose. And I would like to share with you some of my experience and some of the technical challenges that are involved. So what is the motivation behind building a light sheet microscope? So it all started in 2013 in a paper from Carl Deisenholz's lab in Stanford, when they were able to take a mouse brain, as you can see here, and you can see that it's opaque, to make it transparent, as you can see here to the right. The way that they do that, they use a hydrogel scaffold, and then they extracted the lipid out, and they made it optically transparent. Now the problem is, how do you image an entire brain in such a large volume in a fast way? If you're going to use a confocal, it's going to take something like weeks to image the entire brain. The problem is even aggravated as Professor Gradinaru published a paper in which a whole body clearing was able to achieve using perfusion. So you can take the entire mouse and you can clear the entire body of that mouse, as you can see here up. So you had the brain, it took weeks. Now you're talking about the whole body. And it can take months in order to image an entire body using a confocal. So what is the solution? The solution is to use light sheet microscopy. It's a fast alternative to confocal microscope. So here we want to look at very large volumes. We want to look deep into the volume, into the tissue. And we are not that bothered from phototoxicity because the cells are already fixed. So this is the main difference between the previous presentation and this presentation. So in confocal, as I said before, it's a point scanner, so it's very slow. And light sheet microscope, it images the entire plane, and it's something like 100 times faster than a confocal. So the way that the setup works is that you have here the illumination that is coming from one direction, and you illuminate only one selective plane. And that provides you the same effect that a confocal slit provides you in a typical confocal. And the light is detected using a detection objective which is perpendicular to the light sheet. So how you implement it? So the implementation is you can either build it yourself, microscope, as you can see here to the right. And this is Raju Tomo paper. He was the first one that was able to image an entire mouse brain using light sheet microscope. And in many ways, I'm following his steps. And then you have two commercial products, which is Zeiss Light Sheet Z1 and the Ultra Microscope. These are two ways in order to build the light sheet or to buy one. So I want to show you how it looks, the fax acquisition. The fax acquisition is pretty much as the frame that you're going to see in the movie. You're going to see a cleared mouse brain. It's 1 millimeter. You're going to see endogenous fluorescence. So the cells that you're going to see are neurons, and they're going to be white. And in the end, you're going to see 3D rendering. So let's see the movie. Okay, so you saw that we are able to get very fast acquisition, but we can still see the processes and of the cells, and we can get very good 3D rendering of the volume using light sheet. So how it's been done? So this is the light sheet microscope setup, as you can see here. It's a relatively simple setup. We use a laser, and the laser projects the Gaussian beam over the galvanometer scanner. Over the galvanometer scanner, as you can see here. So it's a Gaussian beam. As previously talked, the full width of maxima is usually something like 7 micrometer. And the galvo scanner, it just scans the beam up and down. And that creates a similar effect as using a cylindrical lens, in the sense that you illuminate an entire plane just by dithering the Gaussian beam up and down. And that provides more uniform illumination than using a cylindrical lens. Then the light sheet is projected on the sample, as you can see here. And the sample sits on an XYZ translation stage. Perpendicular to that is the clarity objective, as you can see here. And these are unique objectives. They have very long working distance of few millimeters. And you have a correction color that allows you to correct for spherical aberration. So these lenses are true enablers in order to see deep into the tissue with almost no aberrations or minimal aberrations. And then you collect the things using a camera. So it's a pretty simple setup. However, the synchronization here in a light sheet is quite complicated. You have 3 stages. You have the sample stage, another for the excitation lens, and for the clarity objective also sitting on a lens. You need to synchronize the galvo scanner and the camera. So most of the things are being done on software. So the hardware is not complicated. The software is a little bit complicated. I'm using MATLAB and Micromanager. A lot of people are using LabVIEW. There are advantages and disadvantages to either way. But you need to implement many calibration functions in order to make it work. So what are the important components that you need in this setup? First of all, it's a sample stage. In order to achieve a frame rate of something like 45 frames per second, I'm using continuous scanning. It means that the sample is moving continuously while the camera is capturing images. If you're going to wait until the sample, the stage is going to settle, you won't be able to achieve the 45 frames or 50 frames per second. Clarity objective, I already talked about it, and the camera is also a very important component. So I prefer to use light sheet mode cameras. Currently, Alon has one, and Amamatsu has one, and I would like to explain what are the advantages. So in the standard camera, your readout is bidirectional, as you can see here, and you are able to get full frame and with a frame rate of 100 frames per second. In a light sheet camera, the readout is only in one direction, as you can see over here. So why is it good for us? It's good for us because if you look at the exposure window over here, it's just like a rolling window that goes in that direction. And that fact allows you to improve the SNR of the acquisition, and let me show you how. So you have the light sheet, and this is the sample. You're going to see the light sheet, and this is the exposure window. By synchronizing both the light sheet and the exposure window, as you can see here together, they're moving together in synchronized way, you'll be able to get a better SNR. And the reason is, if you have synchronized motion, you're going to collect the light that is coming from these beads, as you can see here. However, if you would, and you won't collect any scattered light that's coming from other areas in the image. However, if you would illuminate the entire sample at once, you would collect this scattered light that is coming from other components, and that allows you to get better contrast in SNR. So this is continuous scan versus light sheet mode scan. As you can see here to the left, the image is blurred in comparison to the image to the right. So how you synchronize it, and I'm going to give 2 minutes for the people who actually want to build a light sheet, especially that it's not clear from the literature. I'm going to explain how I actually do it. So you have the desktop computer, and it controls an arbitrary function generator. And the arbitrary function generator outputs an external trigger to the camera. So an external trigger is just a series of pulses that when the camera is given one pulse, it integrates only one image. The second signal is going to the galvo scanner. And as a reminder, the galvo scanner takes the light sheet and moves it up and down by according to the voltage that you provided. So the ramp signal that you provided, as you can see over here, what it does is, let's say that we are in the yellow spot over here. So the light sheet is going to be in the upper part of the camera. It's going to be over here. And then if you have the green spot, as you can see here, the light sheet is going to be in the bottom part of the camera. And what you really want to do is to synchronize between the light sheet and the exposure window, as you can see over here. So in order to do that, you have 2 degrees of freedom. Is the ramp slope, which controls the galvo speed, or you can change the delay between the external trigger and the ramp. So the way that I do it in MATLAB, I have a synchronization algorithm. It runs iteratively until it's converged. So you can use any sample. Beads are also fine. You pick 2 beads, as you can see here. This is one bead, and this is the second bead. And what you're doing is you change the values of the delay for each individual bead, and you want to get the best signals that you can. So if we look at the not synchronized case, you will see that the light sheet is in one place, and the exposure window is in a totally different place, so you're going to get a very low signal. But if the delay is optimal, this is your sample, and your camera is going to record that signal. So you change the delay in order to optimize the signal, and you do that for the two beads. If the delay is equal, it means that the galvo and the exposure window are synchronized. If not, according to the delay value, you can change it in order to get synchronization. So you change the speed between them. So that's that. Now I'd like to show you a movie. And this movie, again, I'm going to show you very fast acquisition of 45 frames per second. It's a cleared rat brain. It's endogenous fluorescence, and you're going to see collagenous fibers here. So yeah, let's see the movie. Okay, so I hope that you were able to see the fine processes that we were able to record. In that case, it was 4 tiles that were stitched using a Terra stitcher. And now I want to show you a major issue that I encountered using a light sheet, especially for clear tissue and especially when you're going very deep. The fact is that you need to focus the light sheet to the focus length of the detection objective. So in light sheet, you need to make sure that the light sheet itself is going to coincide with the focus of the detection objective. This thing you don't have in a regular confocal, because in a regular confocal, the light path is shared by, so of the excitation and detection is shared by the same objective. So you don't have this problem. However, using light sheet, you might have the situation, especially deep into a tissue, when you have variation in refractive index, when the light sheet is in one place. However, the detective objective focus is in a different location. And I'm talking about slight variation of something like 10 micrometers that's going to cause the effect of out of focus image, as you can see here to the top. So you need to compensate for that. And the way to compensate for that is to use autofocus in different depths. So it means every time before you're going to apply, you're going to capture a tile, you're going to use an autofocus calibration step. In that case, you just move 0.5 millimeter in 0.5 millimeter steps along your scan, and in each depth you do autofocus. It means that you move your objective location and you look at the images until you get the best contrast for the image. So let's say that we have the position or the value that you get from autofocus from 0 depth, 0.5 millimeter depth, 1 millimeter depth, as you can see here. You build a calibration curve and you interpolate it, and these are the red stars that you can see over here. You use this calibration curve, and then you have a synchronized motion when you scan the sample between your sample that you translated in a continuous mode and the clarity objective. So both of them are going to move in a synchronized way in order to eliminate this out of focus aberration, and all the movies that you saw are using that. So autofocus, you need to think about whether you want to use scatter light versus emitted light, and what focus measure to use. And I have to say that there is no one-size-fits-all solution, especially when you look at different organs. You need to sometimes tailor the autofocus algorithm to that specific organ that you're looking at. So you can always increase the full width half maximum of the light sheet, of course, in order to kind of mitigate that problem. The thing is that if you increase the full width half maxima, you lose the signal to noise and the nice images that you are able to achieve using a narrower light sheet. So I'm using something like 7 micrometer. And just to wrap up, this is autofocus. This is with correction, like the movie that you see, and this is without correction. So you can see that even very small variation of something like 5 micrometer between the detection objective and the light sheet cause severe aberration that you need to take into consideration. So let me summarize about light sheets and some conclusions. It's fast. It creates a lot of data. It's relatively easy to build. However, it's hard to synchronize. It requires proficiency in programming. It's difficult to manage the acquired data. You can either use a computer cluster, and a lot of people talk about the big data problem that's created by a light sheet microscopy, or you can use commercial packages like Imaris or Amira. For Imaris, for instance, I know that it does not stitch the images, and it requires multiple conversions, let's say from stitcher to Imaris and so on. However, the bottom line is that it opens new avenues in biology. You can see very large volumes with a very high resolution and in 3D, and that allows you to look for very rare morphological events. So I would like to acknowledge the people in Professor Gardinaro's lab and, of course, Professor Gardinaro's lab for her guidance, and people in Long Kai's lab that he's hosting. So I'm building the light sheet in his lab, and of course, Antti Linguel for his technical and professional support. This research is supported by these funding agencies, and thank you very much. That concludes my presentation.
Thank you, Dr. Greenbaum, for that fantastic presentation. Now I'd like to introduce Dr. Orla Hanrahan. Dr. Hanrahan has worked with Ondor Technology as an application specialist in life science for the past 5 years. Her role brings her in touch with all of the latest developments and innovations in both camera technology and microscopy applications. Previous to this, Dr. Hanrahan managed a microscopy facility in the biochemistry department at Trinity College in Dublin, where she worked with a variety of microscopy setups, including wide-field fluorescent microscopy, point-scanning confocal microscopy, and spinning disk confocal microscopy. I will now turn it over to Dr. Hanrahan.
Thank you very much, and I'm delighted to be concluding this webinar today, and I'd like to thank our 2 presentations already from Dr. Chen and Dr. Greenbaum. And both of them have been using SCMOS cameras for their light sheet microscopy. So what I'm going to talk about now is Ondor's SCMOS camera and why it is the camera of choice for this particular application. So just moving on then, we'll go to the first slide. And SCMOS detectors are, I suppose, the detector of choice for a lot of applications these days, and especially for light sheet microscopy. And what SCMOS cameras have is they're actually unique in simultaneously offering extremely low noise. So their read noise is inherently very low. So they have essentially 1 electron read noise, and that's without having to use electron multiplication on the chip, which is what is required in an EMCCD camera to enable very, very low read noise. So these SCMOS chips or sensors or cameras have essentially extremely low read noise. They also have very, very fast frame rates. So if you're using the full field of view, so you're using, for example, 4.2 megapixels, which is a huge area. You can achieve 100 frames per second, and that's very, very fast. Now, obviously, if you're using smaller regions of interest, you can go even faster. So you have the ability to get very, very fast frame rates with very, very low read noise. So you don't have the usual problems that you might have with a CCD camera. When you read out very fast in a CCD camera, your read noise is essentially increasing. So the faster you read out, the higher the read noise. However, with your SCMOS cameras, you can read out extremely fast and still maintain a very, very low read noise. Also, with these particular cameras, you have a very wide dynamic range. So the SCMOS cameras allow you to look at very, very low light signals and very bright light intensities in one image. So, for example, if you are looking at deep tissue where you do have a lot of different intensities of light, these cameras are ideal in order to be able to see both the dark and the light in one image. Also, they have a very high resolution. So the pixels themselves are quite small. They're 6.5 microns in size, and you have 4.2 million pixels of this size. So you've got a very large field of view and a very small, the perfect size of a pixel in order to get the best resolution for this type of microscopy. So that's the main features, I suppose, of SCMOS. And in terms of the difference between SCMOS and CCD, the CCD chip is a lot slower than the SCMOS chip. It's also got a higher read noise associated with it. And if you look at this diagram here, the CCD chip is on the left-hand side and the CMOS chip is on the right side, the right-hand side. And in the CCD camera, you have to essentially, in order to get an image read out from the sensor, the pixels have to transfer the charge from row to row, so vertically through the sensor. So each row has to transfer the photoelectrons from row to row, and it's all done row by row until it gets to the very end, and then horizontally sent to the readout register. So it's quite a slow process. However, in your SCMOS chip, every pixel itself is almost like its own sensor. So every pixel has its own readout architecture associated with it. So you don't have to transfer charge from row to row in your SCMOS chip. So everything happens in the pixel itself, and therefore you get much, much higher frame rates. So there's no delays in terms of vertically shifting the charge throughout the sensor. Everything happens in the pixel itself, and therefore you get much, much higher speeds. This then, on the bottom right of this, is an example of your pixel. So you can see that you have all of your transistors around the top of the pixel in your SCMOS sensor. So it's a front illuminated sensor, whereas EM-CCD cameras would generally have back illuminated sensors. So the SCMOS sensor is front illuminated. It means that all of the electronics are covering over the top of the pixel. Therefore, they could affect the actual photosensitive area that's available for the light to enter. So what's on top of every single pixel in your SCMOS chip is a microlens. So the microlens essentially will focus the light inside the photosensitive area inside the pixel. So that's the general parameters with your SCMOS chip. And if we just move on to the next slide, then you can see that the Xyla 4.2 is the ideal detector then for light sheet microscopy. So Andor have a range of SCMOS detectors. We have Xyla 5.5, we have Neo 5.5, and we have Xyla 4.2. And the reason why the Xyla 4.2 out of the full range of SCMOS is the ideal detector is, first of all, because of its quantum efficiency. So it has a 72% quantum efficiency, so it's 12% higher quantum efficiency than the other range of SCMOS chips. And this is because it's a 4-transistor SCMOS camera, and it's because it has essentially lost one of the transistors, or one of the transistors from the pixel has been removed. And it means that you don't have a global shutter readout mode. So the Xyla 4.2 has a 4-transistor SCMOS chip. It's 4.2 megapixels in size. It has a rolling shutter only exposure mechanism. It has less than 1 electron read noise, very low dark current, fast frame rates, and a very wide dynamic range. So I've mentioned the rolling shutter mechanism here, and this is very important in terms of the light sheet microscopy application. Now, with the other SCMOS chips where you have a 5-transistor, you have an additional exposure mechanism which is called global shutter. And the global shutter essentially will give you all pixels being exposed at the same time. So it's a global exposure. So all pixels on the chip are exposed at the same time and all are read out at the same time. I'm going to go into that in a little bit more detail afterwards, but it's important to remember that the rolling shutter mechanism is what is used to synchronize with the light source, for example, in your light sheet microscopy. It's what our previous speaker, Dr. Greenbaum, was discussing. So it's the rolling shutter mechanism of the Xyla 4.2 which is essential for this. So in terms of, I want to talk about the rolling and global shutters here. So these are two important modes. It's important to understand the differences between them, and it's something that is available on SCMOS cameras. So this slide here really shows you the difference between the two modes. So on an SCMOS camera, everything happens from the center outwards in both directions. So it's a bi-directional readout. So the top area here of the slide shows you a rolling shutter exposure and readout. And what actually happens in rolling shutter is that the first row on either side of the sensor will receive light. So as soon as light is emitted from the sample, and if you have your rolling shutter exposure mode turned on, the first row on either side of the sensor will receive light, and then it happens from row by row outwards from the center. And there's a 10 microsecond delay from, say, the first row to the second row, from the second row to the third row, from the third row to the fourth row. So it's a transient exposure. So it's not happening, all pixels are not exposing at the same time. There's a transient exposure happening when you're using a rolling shutter mechanism. Now, if you're not doing, for example, synchronized light sheet, and you're looking at very, very dynamic, large, moving objects, the rolling shutter mechanism might not be ideal for you because it could cause distortion, for example. So you might see a wave instead of a straight line if you were looking, for example, at blood flow. So sometimes in some applications, if you're looking at very, very fast flow movements, the rolling shutter might not be moving. The movement of the rows might not be fast enough, and therefore you see distortion in your final image. However, if you do want to synchronize the rolling shutter mechanism with your light source, this is the ideal method to use. Underneath them we have the global shutter mechanism, and this is really just showing that all pixels are exposed at the same time. They're globally exposed. They're also all read out at the same time, so the readout is global. And this is synonymous with a snapshot mode in a CCD camera. So the Xyla 4.2, which is the camera of choice for the light sheet microscopy application, only has a rolling shutter mechanism. Now, this means that you can easily synchronize to it with your galvo mirrors according to what Dr. Greenbaum explained in his presentation. So the next slide then has two movies, and if you play the movies, we have a rolling shutter and a global shutter movie. Okay, so I'm not sure if the second movie played, but I mean the global shutter is essentially where all pixels are exposed at the same time and all pixels are read out at the same time. So it's really just another way of showing you the mechanism that's taking place on these cameras when you're exposing and reading out. So on the Xyla 4.2 itself, we do have a light scan mode which we've applied, and this is what Dr. Greenbaum was discussing during his presentation. And this is again just a representation of what actually happens. So you're essentially able to control how the camera works. So you have a lot more control and flexibility over the use of the rolling shutter mode on the camera. And what it actually allows you to do, this feature of Light Scan Plus, it allows you to synchronize your scanning light source to a defined scan row heights on the sensor. So you can decide how wide you want this exposure window to be. So for example, you could have it to be as small as one row or as wide as the full chip. So you could decide, okay, I just want 10 pixels or 10 rows of pixels to be exposed. So you set the actual width of this. And what it actually does, it almost looks or acts like a confocal slit detector, and it removes out of focus light. So it therefore provides sharper and more resolved images. So it allows you to improve the contrast of your final images by removing out of focus light. Also with this LightScan Plus mode, you have multiple readouts available. So instead of just having your bidirectional readout, which is the standard readout mode, you also have the ability to use the full length of the sensor and to read out from the top to the bottom or from the bottom to the top. And then you have obviously a few more modes as well on top of that, which will allow, again, more flexibility available to the end user. So this is another movie just to show you how it works. So if we can play the movie, please. Okay, so again, this is similar to what Dr. Greenbaum showed in his presentation, and it's really just to show you how you can synchronize your light sheet to the rolling shutter mechanism on the Xyla 4.2. So what the user has is full control over the pixel row height, the speed with which you can move this slit width on the sensor itself, and also the exposure time. So if you want to use very long exposures, you can use very long exposures and also move the speed very fast, and therefore you're not going to be providing a lot of light to your sample. So for example, if you have very, very bright laser light you're using, you can scan very fast so you're not going to damage your sample. So you can control various different parameters here and giving you additional flexibility. So the benefits of this are that your image quality is improved, and because the scan row height essentially acts as a slit detector, rejecting scattered light, improving contrast and signal to noise, and providing sharper and more resolved images. And finally, I just want to let you know that I know when you're using applications with light sheet microscopy, you generate huge amounts of data. And what we have just introduced recently is a GPU Express, and it's essentially a solution for large data. So it allows you to process data on the fly, and it provides real-time feedback, optimal data throughput, and accelerated frame rates. So essentially, you can take the data that you're only interested in and process that, and it reduces the amount of storage that you would finally need for your data. So it's being, we brought it out to work with the SCMOS cameras for these data-intensive applications like light sheet microscopy. So just like to thank you very much for your attention, and that is my conclusion now for my presentation.
Thank you, Dr. Hanrahan, for that informative presentation. It's time for Q&A. If you have a question you'd like to ask any of our speakers, please do so now. Just click on the green Q&A button at the lower left of the presentation window, type your question in the box that appears on your screen, and click on the send button. We'll answer as many of your questions as we have time for. Okay, let's get started. Our first question is, can we have slides at the end of the presentation? And that would be for either one of you. Okay. I'm hoping you can hear me. I'll just ask you that question one more time. One of the attendees is asking if they can have slides when the presentation is over.
Oh, sorry, yeah. Yeah, so what we'll do, I did hear you, sorry, I have my phone on mute there. We will be providing a recording of the presentation, and Tony, our marketing department, will arrange for these to be sent out to all the people who are currently on the call. So we will send out a recording of this via, in the next couple of weeks, we should have that.
Great. Next question, are any of you familiar with Clarity/Calm? I was wondering if you had any tips for imaging large samples, for example, a full mouse or rat brain.
So I think, Alon, you might know a bit more about that, the clarity question.
Yeah, so I was basically talking about that. Everything that I was talking about, you can take it and you can extend it. So the working distance of the objective that I'm using is something like 8 millimeter. So you can do the same thing. Once you grab one tile, you just repeat the whole process again and again and again until you tile the entire brain. And the major issue using this approach is how you handle the data, because you're talking about terabytes of terabyte-size files that you need to handle them for visualization and in order to do your processing according to the biological question that you have in hand. And this is a Raju Tomer paper that I mentioned in my presentation.
Next is, how big can the live specimen be to use light sheet microscopy? And again, that could be for either of you.
So, Alon, I don't know, you might be better at answering this since you're in the lab. I don't know what size your samples are.
So, yeah, so I just want to mention, so Dr. Chen was talking about in vivo imaging, when you actually have a live sample. In our case, we are using cleared samples that are being fixed. So I'm not completely familiar with his setup, and I'm not completely sure what's the working distance of the objective lens that they are using in order to answer that specifically. So, yeah, I can say that with cleared samples, your main limitation is the working distance of the objective, and in that case, it can be up to a few millimeters. So it depends on which objective they use. And I even have a slide that shows a table with the current available clarity objectives. However, for in vivo application, again, it depends on the working distance of the objective, and I'm not completely sure that I know Dr. Chen's setup, so I cannot answer it directly.
Okay, here's your next one. Is it possible to clear bone and visualize bone marrow in the bone without its extraction?
So I prefer not to completely address this question. This is a direction that we are kind of exploring right now, but there are ways to clear bones.
Okay, we're almost out of time. Looks like we may have time for one last question, and this one is for Dr. Hanrahan. We have a NEO on-door camera, biodirectional, not light sheet readout into the rolling shutter mode, currently installed on our light sheet rig. If I define an ROI in only the upper half of the FOV in an on-door NEO camera, would the readout still be bidirectional, or would it be single directional since the ROI is only defined in the upper half of the FOV? And there's a little more there. I'm going to read it all. Let me know if you need me to read it over.
No, I can
just wondering. They're saying, just wondering if I can apply the light sheet scanning mode in NEO by only using one half of the full camera detector. Will there likely be any software, firmware upgrade for NEO to enable light sheet slit detection scanning mode for NEO?
Yeah, so unfortunately, the light scan mode has only been applied to the Xyla 4.2, so we haven't added it to the NEO 5.5, so it's not possible to use this mode on NEO. And in addition, if you choose an ROI in one half of the sensor, you still have to read out the full chip has to be read out. But if you want to place an ROI and get the fastest readout, you're better off placing it in the center of the sensor and putting it half and half on either side. So for example, if you had a 200 row high ROI that you wanted to look at, and you wanted to get the fastest frame rates, you would put 100 rows on the top of the half of the sensor and 100 rows on the other side of the half. So it has to be sitting on the half, on the center of the sensor to get the fastest frame rates. But you will still have to, so you have to do that, and then the Light Scan Plus mode is not on Neo.
Well, thank you once again. I would also like to thank our sponsor, Ondor Technology, for making today's educational webcast possible. Before we go, I just want to let everyone know that today's webcast will be available for on-demand viewing for 6 months from today's live event. You'll receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That's all for now. Thank you for joining us. We hope to see you again soon. Bye.